All right, let's get started. Hope everybody had a good spring break. Wasn't nearly long enough, right? Hopefully you made the most of the day, though. We will look at a couple of announcements here. The Homework 8 assignment that has been posted early last week is going to be due Friday of this week. And so that's mostly about applying Manning's equation. And then the next phase of your design project, phase 2, which is where you're going to be sizing the pipes, that submission needs to be put into Blackboard by Friday, April 2nd. And we're going to go over a little bit of stuff related to the project today. And in addition to that, I'm going to be posting a demo, a refresher, on how you can use EPANet for hydraulic design. I've been working on an example over the weekend that I'm going to take the time to record and just kind of illustrate how you could solve a network using the loop method and Hardy-Cross approach with a spreadsheet, and then get the same flow values if you solve that using EPANet. So I'll send you the link, and I'll also post that on Blackboard later this afternoon so that you can get started on phase 2, which is pipe network optimization. So once we get through this stuff related to the design project, then the main focus of today's class is we're starting our discussion of topics that are found in chapter 12 of the textbook. And so that's where we're going to begin to analyze open channel flow and look at predicting the depth when conditions are not steady and uniform. Because so far in chapter 10 and 11 we were really just focusing on how to use Manning's equation, which assumes steady uniform flow. But most of the time flow is not steady and uniform. So we need a more robust set of tools for being able to predict the relationship between flow rate, cross-sectional shape, and depth. But first, let's talk about pipe network sizing. This view is just kind of looking up from the bottom at the subterranean environment of water networks, and it's bad if the pipes aren't big enough, because if the pipes aren't large enough, the pressure will be too low and people can't extract the water from the network that they need. People use the water for drinking and irrigation and fire protection, and so it's really important that your pipes are large enough. But of course, we don't want to make the pipes too big because that can be expensive. Now, you've just finished your demand estimation summaries, and your pipe sizing needs to be the larger of the maximum hourly demand or the maximum daily demand plus fire flow. And that was, that requirement is kind of wrapped up in the formatting of the summary table that you've used for your demand estimation. In this next phase, what you're looking for is that your pipe network should be sized such that during peak flow, like when there's lots of demand in the network, during that worst day of the year when the city is completely built out and there's also a fire somewhere, potentially. So when you've got that demand load on the network, then your pressure can go as low as 240 kPa. There are going to be times at night when there is essentially very little flow demand, or maybe even none. And so at the nighttime, when there's less flow demand, you're not going to have losses through the pipes, and so the pressure will be higher. And so we want everywhere in your city to have at least 240 kPa during the peak flow and no more than 850 kPa when there's zero demand. Now let me ask you a question, and this will be kind of a quiz to see who actually has been listening carefully and maybe read the assignment description. What causes the pressure in the network? Like, what determines how high the static pressure is? Static pressure is the pressure when there's no flow demand. So how are you as a hydraulic designer in this project going to govern the upper limit of pressure? Anyone willing to take a guess, take a stab at it? What feature that you're going to be designing controls the network pressure? Water storage tank. The elevation of the water storage tank. Good. That's exactly right. So where you put that tank, do you put that tank way up high on the hill? You know, you could take it too high. If you take that tank too high on the hill, then the pressure in your town is going to go over 850. But if you take the tank too low on the hill, then the problem there is that you're not giving your network enough pressure. And if your network has low pressure when there's zero demand, then when it has a higher demand, it's going to have even worse pressure. So what you want to do is you want to put that tank as high on the hill as you can without going over the limit during static conditions. So your design criteria, you want to make the pipes as small as possible because smaller pipes save money. How do you do that in flat terrain? In flat terrain, you have to elevate the water storage tank. And so you've probably seen, for example, if you're going to the airport in Cincinnati and you're driving through Florence, there's a big elevated water tank there that says, Florence, y'all. There's water tanks in other places too, but that one just is memorable. Or you can do it with pumps. But in this project, just to keep things simple, we're going to assume that it's gravity pressurization from an elevated storage tank. And so it's that elevated water storage tank that pressurizes the network, and the smaller you make the pipe, then the more rapid the energy losses are. Remember that head loss is a function of velocity squared. And if you make the diameter of the pipe smaller, you're increasing the velocity. And so, you know, that's going to increase the rate of head loss. But then also, d, diameter, is in the denominator of the Darcy-Weisbach equation. So the smaller you make the diameter, then you're going to be increasing the rate of head loss. So you kind of have to balance it. This is an optimization project where you're going to look for the just right solution that gives you enough pressure in the demand, high demand times, and not too much pressure in the low demand times. Now, I've given you a topographical map that shows you the elevation of the surface. And in EPANet, you can put the elevation of nodes. You're going to tell EPANet for each junction what's the elevation of that junction. And just to simplify, let's assume that maybe you're going to bury those pipes 1 meter below the ground surface. In phase 1, you were answering the question, how much water does the city need? You were defining the flow demands. You know, you were identifying in terms of liters per second what is your design condition at each of the locations that water needs to be extracted. In phase 2, you're going to be answering the question, what size should the pipe be? And so this is an optimization problem where you are iteratively changing the diameter of one pipe and seeing what does that do everywhere in the network. If you make this one pipe smaller, then you're going to be able to save money, but you have to look at every junction and make sure that now the pressure is still okay. Also in phase 2, you're going to be figuring out where to put the reservoir, because the higher you put it on the hill, the more pressurized your network is. Okay, so you just want to make the pipes barely good enough. And that's the essence of engineering design, is just barely meet the criteria. Because if you over-deliver, then you've wasted money. Because assuming that the criteria are really what the client wants and needs, then if you give them more than that, then you've wasted their money. So anybody can build a bridge, but it takes an engineer to build a bridge that just barely works. And that's what we want. We want it to meet the criteria of, you don't want a bridge that will handle 1,000 tanks driving over it at the same time, because that's never going to happen. You want a bridge that can handle the traffic that will go over that bridge when, when it's actually in use. All right, so now we're going to move back to open channel flow. And the reason why we're doing this is we need more robust tools for analyzing hydraulic circumstances when flow is not steady or uniform. Because Manning's equation does great. You know, by now, hopefully, you're able to solve for the depth in a trapezoidal channel, for example. Manning's equation is great if the flow rate is constant over time, and if you have that nice even prismatic channel and it's not variable in its width and it's not variable in its slope, if it's just a uniform channel that never changes slope or width or anything about it, then Manning's equation is all you need. But if you look at the Ohio River, it's narrow here, it's wide there, it's winding, it has a bend, the flow rate is always changing because yesterday it rained and tomorrow it's dry. So we need a way to predict what is the depth going to be with the real world variability in flow rate and channel profile. So specific energy is the first bit of analysis that we're going to use in order to answer those questions of how deep will the river be today. Now, specific energy is where we are looking at using the bottom of the channel as our starting point, like that's our elevation datum. How much energy is there in the water above that? And what I mean specifically is we're going to consider both the kinetic energy and the potential energy. We're not looking at its chemical potential or anything like that. We're just looking at, related to the fluid flow, how much energy is there. And so E, the specific energy, we're saying it's the depth, and the depth of the flow represents the potential energy that's there. And then the velocity head. The velocity head can be added to the depth because the velocity head has units of length. Think about when we have meters per second and square it and divide that by g, which is meters per second squared. That leaves us with meters. And so the energy itself is going to have units of length as well. This other way of writing specific energy, you can see I've done that same substitution that we've seen before, where sometimes it's not convenient for me to express the velocity head in terms of velocity. Sometimes I know the flow rate, but I don't yet know the velocity. So we can express velocity head as q squared divided by 2ga squared. And remember, alpha is just the kinetic energy correction factor, which for laminar flow would be 2, but for most real-world turbulent flow, the alpha kinetic energy correction factor is 1.05, which is close enough to 1 that we don't even usually bother distinguishing or including the alpha kinetic energy correction factor. All right, now to make this next point, we're going to fire up Excel and address the question, how many different ways, meaning how many different combinations of flow velocity and flow depth can we have when it's a 10 cubic meters per second going through a rectangular channel that has a width of 4 meters. All right, so let me just take a quick screenshot of that, and we're going to paste that setup into Excel, and we'll do some calculations here. I've got the same calculations kind of shown on the next slide, but I think maybe it'll be more impactful if we go through it together and actually set this up rather than just me showing you the data table. All right, so you can feel free to follow along if you also want to calculate this, but if you just want to watch it, then that's okay. Because what we're going to do is we want to look at how many different combinations of depth and velocity are there going to be that have that same flow rate of 10 cubic meters per second. And we're going to look at how much specific energy is there. So rather than just using this same table, I'm going to copy the column titles across the top. Invisible. Copy. Can I copy that? Control C and paste with Control V. All right. Well, flow rate, velocity, area, depth, and specific energy. So flow rate, cubic meters per second. Depth in meters. Velocity. No, we'll do area, meters squared. Velocity, meters per second, and then the specific energy in terms of meters. Okay, so all of the different depth combinations are going to have the same flow rate of 10 cubic meters per second. So I'm going to look at a lot of different depths. So, for instance, we could have that the bottom width here, this is a rectangular channel, which is nice because that geometry is nice and simple for calculating the area, for example. The bottom width is 4 meters. Okay, so maybe, just depending on how steep it is, maybe our depth is 1 meter. Okay, so if the depth is 1 meter, then the cross-sectional area would be the depth multiplied by the width of the channel. And I just anchored that reference so that when I drag it down through, it'll always look up there. Okay, so if the depth is 1, and we know we've got 10 cubic meters per second going through there, this would be the area. Now the velocity, of course, is just flow rate divided by the area. And now the specific energy, we're going to use this formula here. It is the depth, y, plus, I'm going to ignore alpha. I'm going to say velocity squared divided by 2 times g, 9.81. Okay, so this is how much specific energy there is if the depth is 1. Now, let's say, what if the depth is 1.5? All right, and I can just drag all the rest of this down for a depth of 1.5. And maybe, where did I start when I was doing this? I started with a depth of 0.25. All right, so let's start even lower than 1. 0.25. I'll go 0.5, 0.75, 1, 1.25, 1.52. We're just going to get a whole variety of different depths, and there's really an infinite number of possibilities. Went as far as a depth of maybe 1.5 at the upper limit. So that I have a little bit more resolution, I'm going to do smaller steps. So I was doing 0.25. Let's do this. Just increments of 0.2, then 0.4. All right. Now, the interesting thing to see is that there's a minimum specific energy. So we have an infinite number of possible flow depths. Like you could have the water moving very fast. So if we had a steep slope, if we sent 10 cubic meters per second like down a really steep slope, the water would be moving fast and it would be shallow. So this, at the one end of the scale, these first values are related to a very steep slope, like water not going off a cliff, but going down a steep chute. On the other end of the extreme is if we had a really shallow slope and a greater depth, then you still get the same flow rate. You still get the same Q of 10 cubic meters per second, but the velocity is very low, right? So if you've got deep flow, then it doesn't need to be moving at the same V in order to have the 10 cubic meters per second. Now, the important thing that we want to do is we want to say, what is the minimum? Because, you know, it starts high. At this end of the scale, like, why is the specific energy high? I'm just going to put in some notes here. Some notes so we are all on the same page. Like this is, at the top of the chart, represented steep channel, high velocity, low depth. Now the specific energy equation, which is here, most of the energy that we have is from the velocity. So I'm going to say most of the energy is from velocity head. Because we've got 8.16 meters of energy, and only 0.2 of that is from the depth. So like there's about 8.2 meters of head, and only 0.2 meters of it is from the depth, and the vast majority is because it's got so much kinetic energy, because it's going on such a steep channel. This, on the other hand, would be a shallow slope at this end of the extreme. Low velocity, high depth. So there's 2.8 meters of depth, and now look at this equation for specific energy. If we've got a total of 2.841 meters of energy, and 2.8 of that comes from the depth, that means that it's only 0.041 is associated with the velocity. So there is most of the energy is from the depth. Very low kinetic energy. All right, so that's the first lesson I want you to take away from this analysis that we've done, is that there's an infinite number of combinations of depth and velocity, and at the one extreme you have a lot of kinetic energy, at the other extreme you have a lot of depth, but somewhere in the middle here we could find where's the minimum, the lowest energy. So we're pretty close to it here, but what if we wanted to minimize? If we wanted to find the smallest possible? I'm not sure if I have Solver installed on here, and boy, it's been so long that I actually even used Solver that I am reluctant to do that tightrope act of demonstrating with it. But options, I think it's in options that you turn on Solver. Add-ins. Come on, where? Not responding. Okay, here we go. Solver. Manage. Okay, I'm going to turn on the Solver add-in. I want to find out what depth gives me the lowest minimum. And I can't use goal seek, because goal seek really only works if you know what you're looking for. And I don't know what is the lowest specific energy. So let's try and see if I can use Solver. It's on the Data tab. There it is, over here. Now I see Solver. So what if analysis goal seek wouldn't work? Because my objective is going to be, I know that 0.8 is pretty close to the depth that gives me the lowest specific energy, but what, is it 0.79 even lower? No, it's not. But what about 0.81? Yeah, 0.81 is even better. So I'm looking for, like, what is the specific, or what is the depth that gives me the lowest specific energy? So over here, now if I go back to Data tab and Solver, then I want to minimize. So set objective. My objective is that this specific energy is minimized by changing the depth. Okay, so now when I say solve, it tries a lot of values and it's just looking for which one was the lowest. It's going to remember when it saw the lowest. There we go. Over here it gave me the results. It says, do you want to keep your original solution where it tells me the depth that is associated with the lowest specific energy is 0.86047? Yeah, I want to keep that. So okay. This is a special thing. This is the minimum specific energy. It means something. Let's talk about what? Let's go back to the slides here. Any questions so far, by the way? Any questions at all? Okay. Okay, well, let's do a couple of graphs. I know I've already got them made on the next slide, but I think demonstrating them for you will potentially make an upcoming homework problem a little bit easier. So let me demonstrate both flow depth versus flow velocity, but then also more importantly the specific energy diagram. So we could graph, so I'm going to insert a graph here. I'm going to insert a graph and I'll connect the dots here with a smooth line just so it looks pretty, and I'll insert my data. Computer's being a little bit laggy here. Chart design, select data. Alright, so I want to have in my x value, I'll go for the depth and velocity on the other axis. So here is my depth, and I'll give that a label. Oh, I'll have to label that later. It's depth and versus velocity. All right. Let me turn on the axis titles. Depth versus velocity. And here I've got velocity in meters per second. And here is the depth in terms of meters. Now, when this is a good graph, it just shows that you can either have a lot of velocity or a lot of depth to accommodate the same flow. And that's kind of, some of the same conclusions we came to here in the notes. The more interesting thing for us to do is to generate a graph of specific energy versus flow depth. And so I'm going to insert another chart here. In fact, I'm just going to copy and paste this one, and then I'll adjust what it's looking at. So Control C and Control V. So this is going to be depth versus specific energy. So all right, and we will have depth and specific energy, except for I want to switch the two. So I want on the vertical axis, I want that to be, oh no. Okay, so the vertical axis, I want to be the depth. There it is. All right. So vertical axis is depth in terms of meters. So depth y, in other words, y in terms of meters. And then here is the specific energy. Well, it also has units of meters. All right. Now remember, we said that this is the minimum specific energy and it had a depth of 0.86. You'll notice that is the lowest specific energy. That is a critical point. We could zoom in on this, like if I change the scale of the graph, let's say that I only have it display up to a maximum of 4, and that'll allow me to zoom in, right? If I change the range of the horizontal axis, now I'm zooming in a little bit. Here is a really important point. It's called the critical depth. So critical flow is something that you've done just a real preliminary estimation of on one of your homework assignments. When the water is flowing at the y sub c, we call that the critical depth, and that's the depth that generates the lowest specific energy. So if we go back to the conclusions we've drawn here, this is the minimum specific energy. The critical depth is 0.86047 meters. That depth yields the lowest specific energy for this channel and flow rate. Critical depth. So it is the depth that in a way is most hydraulically efficient because you're getting the energy through the channel with the lowest amount of energy required. If the depth is more than the critical depth, then we call that subcritical flow. And if the depth is less than the critical depth, that's supercritical flow. And that maybe is a little bit counterintuitive to you. But the sub and the super isn't so much referring to the magnitude of the depth as it's referring to the velocity effects. And so when you have a low depth, the water velocity is fast, and so that's supercritical. So back here in our diagram, anytime the depth is less than the critical, these are supercritical depths. So this is the range of our flow possibilities that are supercritical because we had the fast velocity. So fast velocity, low depth, that's supercritical. Then here's our critical flow. And then anything below that, this is where we had a big depth, lower velocity. So this is subcritical part of the range. What would happen if you split the flow rate in half? Through the same channel? I don't know, let's see. So if we have only 5 cubic meters per second. Okay, so here we can see that we've got a new, it looks like a new minimum, like the minimum isn't in the same place as it was before because look at this. This is lower. So I mean the notes didn't update automatically, but if you have a different flow rate, then you're going to have a different minimum depth. It's going to reduce the minimum depth. I'm going to go back to the original 10 cubic meters per second. Okay, so just talking about the classification. You can either classify the flow regime by depths, or you can classify the flow regime by calculating the Froude number. And I think you've done Froude number before. Do you remember calculating the Froude number in a previous assignment? There's a couple of different equations for it. So this particular version of the equation may not yet look familiar because the previous version of the Froude number equation that I gave you I think was specifically for a rectangular channel. This is valid for any channel geometry, whether it's trapezoidal or whether it's rectangular or circular, triangular, anything else. This Froude number equation, you take the square root of both sides, and so the square root of q squared times b, the top width, divided by g times a cubed, that'll give you the Froude number. And if the Froude number is less than 1, the flow regime is subcritical. And if the Froude number is greater than 1, the flow regime is supercritical. So today, if your parents or friends ask you what you learned about, tell them you learned about supercritical flow. It just sounds like you've really been in the thick of it today, like learning important stuff. If you're learning how to calculate supercritical flow, your parents will really feel like they're getting their money's worth out of supporting your education. All right, so this flow classification, you may wonder, like, is there a point to this? Is it just an academic discussion? Are we making these graphs just for like no reason? The reason it is important is that whether the flow is supercritical or subcritical has a big effect on how the flow reacts to things like obstacles. Like if you drop a big rock into a channel, so now all of a sudden you've got a non-uniformity. If you put an obstruction in, then the way the water behaves is different if it is supercritical flow or subcritical flow. So that's why we're kind of laying a foundation of understanding the flow regime. It's the key to being able to predict how the depth is going to change to things like a change in slope, or if the channel is getting wider, whether it's supercritical or subcritical is going to be a key factor in understanding whether the depth increases or decreases. So this specific energy diagram, I'm going to label this as a specific energy diagram. You're going to have to make these And you could classify the flow. Now think about, we could do a dividing line. I'm going to insert a couple of little shapes here to make it obvious that here is our critical depth. Alright, I need to make that level. It drives me crazy if it's not exactly level. There we go. Whew. Crisis averted. Oh, I just blew it. 0. I thought I said, okay, there it is. Let me zoom in on this. Alright, now I'm going to take that up a little. Alright, so anything above that line is the subcritical region of the figure. So up here, flow is subcritical. Okay, so that is the region of the figure where the flow is subcritical, and then I'm going to make this little comment below that. I copied it. Control C and Control V. Alright, so down here, flow is supercritical. So you could make this figure, and if you knew, your channel geometry and the flow rate, then you could diagnose your flow regime by comparing the depth to what zone of the figure you're in. Like if the given depth is 2 meters, then you'd know flow is subcritical. If the given flow depth is 0.5 meters, then you'd know that the flow is supercritical. One of the interesting things is that there can be 2 depths that have the same amount of energy. All right, so take for example 2 meters of specific energy. There is both a supercritical depth that gives you 2 meters of energy, and it looks like it's what, maybe 0.45 meters. So you could have 0.45 meters of depth give you 2 meters of energy, or you could have what looks like about 1.85. Let's just find exactly that. Let's go back over here and find what are called alternate depths. Alternate depths are 2 depths that have the same amount of specific energy. So if I want to find out what depth is associated with 2 meters, let me try, I guess I could use goal seek this time, right? Because I do know what energy I'm going for. So data, what if analysis, goal seek. So if I wanted to say, set this energy to 2 by changing the depth. Okay, so I'm finding the supercritical depth that has a specific energy of 2 meters. And then down here, I'm going to find the subcritical depth that has a specific energy of 2 meters. Okay, so I'm going to set this to a value of 2 by changing this depth. All right, so 0.45 meters of depth and 1.91 meters of depth, they both have the same amount of energy. Same amount of energy, 2 different depths. Those are called alternate depths. Oh, was it on this slide that I... Alternate depths. 2 depths that have the same specific energy. All right, so we've gone through the process of identifying the critical depth. We've gone through the process of identifying the range of the graph that is supercritical, the range that is subcritical, and the last point I want to emphasize before we move on is that it's the slope of the channel that determines whether you're having critical, subcritical, or supercritical flow. And then those 2 different depths that have the same amount of energy is called alternate depths. And the reason why I want you to know about alternate depths is there's this awesome thing called a hydraulic jump. And if we were meeting in person, we'd go down into the fluids lab and we'd fire up the flume. And we would look at the hydraulic jump. I may have to make a video of the hydraulic jump and show you what happens. But the flow can be supercritical and then jump up to its subcritical alternate depth. And actually water does that after flowing over a spillway, like at a dam. It's got a lot of energy, and then it can't sustain that fast-moving, shallow, supercritical flow, so it jumps up to its alternate depth through a hydraulic jump. So it's a really interesting phenomena, but you can predict what the alternate depth is going to be with this specific energy diagram. Okay, so we've gone through the definition of Froude number and how to classify the flow regime. Hydraulic depth is something that I've introduced before, and it's simply just the ratio of the top area of the channel, of the area of the channel to the top width. And so here's the formula for the hydraulic depth. Of a rectangular channel, the hydraulic depth is simply just the depth itself, because it would be B times Y for the area, and then if you're dividing by B, then all that's left is Y. So the hydraulic depth of a rectangular channel is the depth itself. Now, I also put in this preliminary note here, and we're going to talk more about this in the future, but if a channel is really wide, meaning that its width is more than 20 times greater than its depth, then the hydraulic depth is also just equal to its depth, Y. And the reason for that is that, think about this channel. I'm just going to make a copy of this slide and modify something so that I can show you the extreme. What if it's really, really wide? Like, what if this is way over here and we make this channel rather long? Okay, and the water is all the way to the top. So if we make that channel really big, then it doesn't matter so much this little area in the side. Like the edge effects of the amount of flow area in the triangles on the side is relatively insignificant. And so that's where that note comes, where we're talking about if you have a very wide channel, then the hydraulic depth is equal to the depth, is because these side areas become relatively insignificant when you have a really wide channel. And the reason why that's useful is that sometimes we'll use hydraulic depth in our calculations, and it'll just be simpler if we just assume that it is the flow depth. And that's a valid assumption if the channel is more than 20 times wide of its depth. All right. We've just got a little bit of time here, so I'm going to pause for a second and ask you to use the Froude number equation. Here it is. I'm going to give you a chance to calculate if you've got a flow depth of 0.25 meters, is the flow supercritical or subcritical, and what is the Froude number? And then same with this depth of 1.25. So calculate the Froude number of each. Now you could diagnose whether it's supercritical or subcritical. You could diagnose it with the specific energy diagram. But let's verify it by calculating the Froude number. So I'm going to pause for a second and give you a chance to calculate the Froude number for both of these flow depths with a rectangular channel. Okay, so you can see here the Froude number for the first case is 6.38. So that, just from the Froude number alone, will tell us that we have supercritical conditions. But looking off of the figure, we can also tell, because here's our specific energy diagram. Here's the minimum specific energy, which is the critical depth. So any depth less than the critical depth is going to be supercritical. And so if it's a flow depth of 0.25, that's below the critical, which is 0.86. So we know it's supercritical both from the figure and also because the Froude number tells us that's greater than 1 means supercritical conditions, whereas this other depth, 1.25, is a deeper depth than critical. So from the depth, we could also diagnose that it's a subcritical flow regime. But then the Froude number confirms it, because our Froude number is less than 1, and that confirms that we have supercritical conditions. Any questions about that? Well, I think that's it for today. Let's take one last look at these announcements here. Okay, your homework aid is due on Friday. This afternoon I'm going to be recording a demo on EPANet. I'll try and get it edited today and uploaded to YouTube and email you the link so that you can start the design project phase 2. That's all I got for you today. I hope you have a good one. I'll see you next time.